Welcome back to Software Engineering 2FA3 Discrete Mathematics with Applications 2. We're going to continue with the topic of predicate logic, and today we're going to talk about theories in FOL. Remember, FOL is our version of first-order logic. So a theory is a pair, as you can see here, where this is a signature, this is a signature, and this is a set of sentences of that signature. The signature, as you know, determines a set of constant symbols, function symbols, and predicate symbols, and this set gamma is going to be a set of sentences, and these are called the axioms of our theory. Now, M is a model for the theory, which we write like this. If M is a model for gamma, and A is valid in a theory, which we write like this. If A is a logical consequence of gamma. And we say our theory is satisfiable if it has a model. So there's many examples of theories. A theory of FOL is a first-order theory, so we have theories of orders, lattices, Boolean algebras, theories of monoids, groups, rings, and fields. These are algebraic theories. We have first-order Peano arithmetic. This is a theory of natural number arithmetic. And we have the theory of real closed fields. This is basically the algebraic theory of real arithmetic. Okay, so we're going to look at some examples of theories. And the first example is a theory of strict partial orders. So we're going to look at this signature where there are no constant symbols, no function symbols, and just one predicate symbol, a binary predicate symbol. And we have these three axioms. The first says that the values in our domain are irreflexive with respect to less than. And number two says we have the asymmetric property. Number three says we have the transitive property. And you know now that if a set with less than has these three properties, it is what we call a strict partial order. So this theory is a theory of strict partial orders, and the reason we say that is that every model of this theory is a partial order. And we can think of every partial order as a model of this theory. So the models of the theory are the set of all possible strict partial orders. And what this means is if we know that this is true, so this is saying that A is a theorem of T, or in other words, A is a logical consequence of the axioms of T, then we know that A is valid in every strict partial order. So by reasoning within T SPO, we're able to reason about all strict partial orders simultaneously. And this is really the power of the axiomatic method. Okay, so here's a question for you. Take a moment and think about it, and I'll come back. Okay, here's the question. Suppose M is a model of our theory of strict partial orders. Which of the following statements is true? Well, if M is a model of this, M is going to be it's not going to be a weak partial order. Remember, weak partial orders and strict partial orders are closely related, but they satisfy different properties. It is going to be a strict partial order. It says M is not a strict total order. Well, it might be a strict total order. May not be, but it might be. And the last is M is a strict total order if this statement which is the trichotomy statement, if this statement is valid in T. So those are the two statements that are true. Okay, now we have another question. Every theory has a model. Is this statement true or false? I'll give you a moment to think about it. Well, welcome back. It's false. A theory does not have a model. So let's take a simple example. Let's go back to our theory of strict partial orders. And let's say I add to it another axiom. The axiom is, for all x, x does not equal x. If I add that as an axiom, then this axiom will never be valid in any model. Because remember, our models always have at least one element, and that one element equals itself. So if we just add this single axiom to our theory of strict partial orders, so we can think of it as a theory of strict partial orders with this statement, then it will not have a model. So theories do not have to have models. The thing about theories that do not have to have models, we call these unsatisfiable theories. And they're really pretty useless. There's not much benefit in having an unsatisfiable theory. The problem is, it's not always easy to tell if a theory is satisfiable or not. The simplest way of telling is to demonstrate that it's satisfiable by producing a model. Okay, so let's look at another example, a theory of monoids. So a monoid is a very simple kind of algebraic structure. We have one constant symbol, one binary function symbol, and we have no predicate symbols. And it satisfies these three axioms. The first says that our operation here, our binary operation, is associative. So this is associativity. And E is a left identity element. What that means is if I multiply something by E on the left, I get the thing I'm multiplying by. So it's a left identity element. And in 3 says E is also a right identity element. So any set of values that satisfies these three axioms is called a monoid. And so this is a theory of monoids. And monoids are all over mathematics. They're all over computing. We find them everywhere. So here are some examples. We have the natural numbers with 0 and plus is a monoid. And what we really mean by that is, remember, a model is D plus an identity element. So when I write this down and say it's a model of T, what I'm really saying is D is N, and I is a function that maps E to 0, and it maps dot to plus. So when I claim this is a model, I'm really saying, well, this is the domain, and there's an identity or interpretation function, I should say, interpretation function that maps this symbol E to 0 and dot to plus. So this is a monoid because plus is associative and 0 is the identity element. If I add 0 to anything, I get back 0. Oh, excuse me, I get back x. I don't get back 0, I get back x. Likewise, the natural numbers with 1 and times is a monoid. We can see that because times is associative, and 1 times x equals x times 1, which equals x. And there's many more monoids like this. There's the integers with 0 and plus, and so forth. Now, another example of a monoid is a set of strings. So let's say this is a set of strings, and we have concatenation and the empty string. And if we write concatenation by plus plus, the empty string concatenated with any string equals that string concatenated with the empty string, which equals S. So yes, this is a monoid. And an integer list, a list of integers, is a monoid where append, it's like concatenation, and the empty list is a list that has no elements. That's also a monoid. We also have a monoid if we take all the functions from u to u and we have function composition. So function composition, it depends how you like to define it. You can say if f and g are two functions and we apply those to x. The way I like to do it is this will be the result. That's because if we have u, so we have u, and this is f and g. So we have f composed with g. It works this way. But also people will sometimes want to define it this way. You can define it either way. So really, there's two ways. There's 1 and 2. But anyway, either way you define composition, the result is that composition is associative, and the identity function, the function always maps a value to itself, is the identity element for this monoid. Okay, so we can see that a monoid is a simple kind of algebraic theory. Its models are algebraic, first-order algebraic structures, and there's many different kinds. Okay, so I have another question. This is about theory extensions. So let's say I have T and T prime, and T prime is a theory extension of T, but notice they both have the same signature here. So the only difference is T prime has more axioms, additional axioms than T. And so which of the following statements is true? I'm going to give you a moment to think about that. Well, let's go through these. Every model of T is a model of T prime. Well, yes, if we, well, no, I said yes, but I should have said no. No, because remember T prime, if we add a contradictory axiom like I just mentioned before, one like this, if I add that axiom, by the way, when I write this, I really mean, this is how it's officially written. If I add that axiom, then T prime would have no models. And so if I have a model of T, then it can't possibly be a model of T prime because T prime would have no models in that case. So this is not true. The second one is true. If I have a model of T prime, that means those models satisfy all the axioms of T prime. So they must satisfy all the axioms of T. So this is true. Now if T is satisfiable, then T prime is satisfiable. This is not true because of the same reason. If T prime has a contradictory axiom, then it will not be satisfiable. And if T is satisfiable, that will not mean that T prime is satisfiable. But going the other way is true. If T prime has a model, that means that model satisfies all the axioms of T prime, which means it also satisfies all the axioms of T. So this is true. Okay. Now we're going to look at a different kind of theory. Remember when we looked at the theory of strict partial orders and the theories of monoids, those theories had a lot of different models, different kinds of models. In the first case, different kinds of strict partial orders. In the second case, different kinds of monoids. So now what we really want is a theory just about, we want a theory about the natural numbers, the zero, successor, plus and times. So this is an algebraic theory. We want a theory of this model. So this is a little different. We're not interested in a theory that has lots of models. We're in a theory that just has this model. And here's our signature. We have 0, the successor function. Remember, the successor of x is just going to be x plus 1, and we have addition and multiplication. And then we have the following axioms. Now, basically, if you remember, when we defined NAT had two constructors, 0 and successor. So we basically would like to simulate, an inductive set that we define with NAT. So 0 and S are going to play this role. And the first two axioms here, they say that we have no confusion. They say 0 is never equal to successor of anything. And if we have the successor of two things, then those two things must be equal. It's not possible using 0 and successor to basically construct two different, the same value in two different ways. Okay, so it looks like we have, so this is no confusion. And then we have the recursive definitions that we've seen before. So this is plus, and this is times. We saw these before when we talked about NAT. So these are definitions of plus and times, defined basically recursively using pattern matching. Okay, everything's okay, but we also would like to have no junk. And in order to have no junk, the axiom we need is the induction principle. We need the induction principle. And the induction principle need to start with for all properties, and it's really for all properties of natural numbers. I should say we can say properties are predicates. Wait, this is false and true. That's how the induction principle starts, for all properties. But notice property is a higher order value. And we cannot quantify in first order logic or in FL over this. So we cannot express the induction principle. And therefore we cannot capture the notion of no junk. So this means we really can't define this structure as an inductive set, because we cannot express an axiom that says there's no junk. The axiom, we know what the axiom is. It's the induction principle, but we can't express that in first order logic. So what we do is we approximate this, and we write, instead of one formula, we write a whole infinite set of formulas where we get a different formula for every formula B of our signature. So normally we would put a property here, but here we put B. And what we mean by B is I replace all the free occurrences of x with 0. I'm using substitution. Here I just mean B with x. Here I mean B where we replace x with successor of x and so forth. So this is an approximation of the induction principle. This says that the induction principle holds for all properties that we can express with a formula. Unfortunately, there are many, many properties we cannot express with formulas. We don't have enough formulas to express every property. So this is just an approximation. And as a result, that means there will be other models of this theory which are not going to be this model. These are so-called non-standard models of arithmetic, or models of PA. Non-standard. And you may wonder what they look like. Well, the most important thing is they have natural numbers which are infinite. In other words, natural numbers which are bigger than all the standard natural numbers. So this is a very important theory. It's the theory people use when they want to talk about natural number arithmetic in first order logic. And this is called first order Peano arithmetic. Okay, so we have one more thing to talk about. We can think of a mathematical structure as a concrete mathematical model. So mathematical structure Now, mathematical structures are more general than first-order structures, but we know with a first-order structure, it has a domain, and then it has some distinguished values. And these distinguished values all are either members of the domain or they're functions or predicates over the domain. And if we have a more general mathematical structure, it can have a whole bunch of domains. And these distinguished values can be more general. They can be more general than just being members of these domains or functions or predicates over these domains. So a mathematical structure we can think of as a concrete mathematical model. And a theory we can think of as an abstract mathematical model. And in mathematics, people often jump back and forth between theory and structure. And they're often not clear that it's not clear to the reader or the audience that they're jumping back and forth. In logic, we will be much more precise. We will make a precise distinction between theory and module. And we can think of a theory as a specification of its modules. It specifies its modules. And there's a nice analogy that a theory is to a model like a software specification is to a software implementation. And many times when people write software specifications, they essentially represent the specification as a kind of theory. So we've seen theories fall in two categories: those intended to specify a single model, like the natural number arithmetic or real number arithmetic. Our example is first-order Peano arithmetic. Or a theory specifies a collection of models, and our example is a theory of monoids. Okay, we'll stop here, and we're going to continue with proof systems next time. See you then.